attempt to solve Ax equal to b, right, would be, let's say this is m cross n, so there are n columns, right? A is this, bn, right? Remember, we wanted to solve this problem, and from whatever we discussed, the first thing should be, if we want to solve this, first we should find a basis of the space spanned by C1 to C, right? This might be a good idea, right? Why if Cn can be written as a linear combination of C1, then it's kind of useless for us. So we can throw it out. We can make our problem simpler. We can reduce the dimensions, right? And if we reduce it to 2, great, then we can use the graphical method, right? But obviously it seems like a good idea to kind of condense this matrix, and that we can study irrespective of this and this, right? And so let's study matrices. The first thing we want to talk about for matrix is linear operators. And can someone tell me what are linear operators? Okay, what is an operator? Function on vectors. So what is a linear operator? Some constraints. Okay, yes. So operator means I am looking at some function or some operator from a vector space V to vector space W, right? Operator means for any vector V here, there is a image from vector space W, right? And then if I talk about linear operator, that means a linear operator acts linearly. Right? Good. Do we know any example of linear operators? Good. So how are they linear operators? What are they? Which space are they going from, and what space are they going to? So let's say my matrix M is some M cross N matrix, right? You said it is a linear operator, right? I agree with you. But if it is a linear operator, it is going from V to W. What is V? What is W? Is also, no. V is Rn and W is Rm. It takes a vector. Remember, Ma equal to B. This has to be n cross 1. And what we get is n. Correct? So M is basically a linear operator. You can check. You know that agreed? And again, one of the fundamental theorem is when you hear of linear operators, when you hear of matrices, very nice. It's not just that matrices are examples of linear operators, but every linear operator has a matrix representation, right? Now, someone says they have a linear operator, and you want to know that linear operator. How will they give you the linear operator? By set of equations. How okay? What equations will be there? No. Remember what is linear operator? It's a function from V to W. Right. The dumb thing would be to take all possible elements of V and give its output. But that's going to be a long list. Exactly. So this is another fundamental thing that and this is true because we have a linear operator, right? So once I give you the action on the basis and I want to know, okay, what is the action on V? I will first write it as yes. So let's say my basis is B1 to Bk, right? And I want to understand what Fv is. Then f of V can be written as this because B1 to Bk is a basis, and then this is and someone has given you these values on the plate, right? So you can compute this thing. That means, as Soham said, if you know the action of the basis, then you know the action on the entire vector space. Correct? Okay, great. Now I have a way to give you the linear operator. And every linear operator has a matrix. What is the matrix corresponding to this? Very good. So the question to ask is, so every linear operator has a matrix representation, and this is something which we forget. Once we fix a basis. Okay? And then, since you answered so nicely, I give you the freedom to choose any basis of your choice. So I think Dev knows the answer, but what about others? Fix your favorite basis. What will be the matrix for this linear operator? You can. How can it be identity? That is not correct. I'm not saying V1 is equal to W1, V2 is equal to W2. So you have to find a basis such that you can easily write it in the matrix representation. So which basis will you choose? And how will you write as a matrix? Again, we are doing these exercises so that you become familiar with linear algebra, right? That's the aim. So think about it. Okay, let me simplify the problem for you. You know, we want to, sorry. I want to write the thing in this representation. Okay. So then, when I write this as k coefficients, these are the coefficients of V1 to Vk. Okay. And I should get the corresponding W. What is M? Right? Yes. What are the entries of M? So here I will give alpha 1 to alpha k, and when I said that my matrix is written in this basis, this is what I mean. Sorry. So I choose my favorite basis here on which I am applying, and here also I apply my favorite basis. Like, did I do something wrong? No. Yeah. Sorry, alpha is are scalars. Yes. W1 as? No, W1 you cannot write in terms of Vi. This is your matrix representation. And the idea is this times this is exactly this. This is the way to interpret your matrix multiplication. Right? So when you write MV, and these are the columns. This is this is how we multiply matrix with a vector. You can convince yourself. Okay. So then, this is the matrix which captures the linear operator. Good. We wanted to talk about Ax equal to b. A was a matrix or a linear operator, right? And we want to find out, is there a vector x on which I can apply A and get B? This is the question we are asking. Okay. So and then if you want to study this, obvious things to talk about are the image and the kernel of the matrix. What is the image? Image is the set of all y right. So then we are asking, is B part of the image of A? Okay, and kernel is the did I do something wrong? Right? So it's the set of all y's such that there exists an x. Ax is equal to y. Make sense? Is this okay? Is this mathematical notation okay with you? Right? And this is the image, and the kernel, it's the set of all x such that Ax equal to C. Okay. And then if A is a linear operator from V to W, then image is in which vector space? W, right? It's a subspace of W, it's a subset of W. And not just that it is a subset of W, actually, if we have two elements of the image, we take their linear combination, it still is a element of the same subspace. So image is a subspace of W, kernel is a subspace of Does anyone have this question in mind, why image and kernel are vector spaces? This is okay? Sounds good? Okay. So then the next concept is rank of a matrix, which is basically the dimension of image. Okay, and one reason to reduce kernel, and you will see it behaves very nicely. It's kind of the orthogonal part of the image. I don't want to say orthogonal because they are coming from a different vector space, but they are complementary to each other. And one of the way to put it is the rank-nullity theorem. right, which says dimension of image of M plus let's say M is an M cross N matrix, so V is R to the N. How do we prove it? What will be your attempt to prove this? This everyone knows this, right? Rank-nullity theorem. Yes, no. Is there anyone who was seeing it for the first time? Okay. There is no shame in saying yes for this question, right? All of us have some flaws in our background. It's okay, but I need to know if this is new to you. Okay, if this is not new to you, then you should be able to prove it. And let me start with, so now this is, let's say this is a basis of okay, and then I want to create a basis of image of M. What size should it be? Okay, I think I have helped you enough. Now, can you tell me? How many people know the answer to this? One. Okay. Others? So if I'm given a basis of V1 to Vk, how will I create a complete basis of the vector space? You remember this diagram, right? This nice diagram. Take one. If it is not, you take another one. If you still didn't get the maximum independent set, another one, right? And we were given a guarantee that every time we will stop after n, after we have picked n vectors, right? So why don't we start with that? So we have V1 to Vk. This is linearly independent because it is a basis. Let's find something which is not in the span of V1 to Vk. Okay. Now can you tell me what is the basis of image of M? You are giving a wrong answer, but I know you know the right answer. What is A? I don't know what A is. But, okay. Remember, it cannot be Vk plus 1 to Vn. Why can't it be Vk plus 1 to Vn? It's the wrong space, right? I have to go to the W. And what is the way to go to W? Apply M. Okay? So my claim is that this is the basis of the image. Okay. What do I need to prove for this? You tell me what do you need to prove for this, and then I won't ask you to prove it. Wait. Let anyone else answer. What do I need to prove? The back row is out, this row is out. Only either you guys or you. What do I need to prove to show that this is a basis of image of M? How do I prove that something is a basis? Linear? Okay, good. So I have to show anything here can be generated using these vectors. What else? Wait. What else do I need to show for it to be a basis? Yes. And both these parts are easy. If you can't do it, once again look at some linear algebra text. Okay? This is basically saying that some linear combination of Vk plus 1 to Vn is in a kernel of M, which is a counter example, which is contradiction, right? And this will use the fact that you can write any vector as a linear combination of V1, V2 up to Vn. Okay, so both these parts are okay. But I leave it as an exercise. All of you should make sure that you can do this. Great. Let's move on. Let's see more properties of image of M or the rank. So the rank was the dimension of image of M, right? But I also know that image of M is linear combinations of what should come here? Columns of M, right? We just saw what was M times V. It was basically taking linear combinations of the column. So this is columns of M, right? That means my rank of M is equal to number of or maximum number of linearly independent columns. And if you believe in the sanctity of this world, then this should also be maximum number of no, there is no good reason to believe that this is equal, but we know that this is actually equal, right? So we know that column rank is equal to row rank. And if you are seeing this thing for the first time, this should surprise you. There is no good reason to believe it, right? So you have a matrix, you can view it as bunch of columns. How many linearly independent columns are there? Or you can see it as a collection of rows. How many linearly independent rows are there? It turns out that this is going to be the same number. How many people have seen this before? How many people have not seen this column rank equal to row rank? Okay. Okay. So now people who have seen it, what is the, any answers? Any two-line answer? Any two words answer? Yes. Okay. So one of the natural proof which comes, which proves this is Gaussian elimination, but I'm going to give you a two image proof. Now you can say it is two image or one image, that is up to you, but I think that will highlight why this is true. Okay, so suppose the column rank is k. What does that mean? Everything here can be represented in terms of k columns here. Let's say some C1 to Ck. There is some linear combination here which will give me C1. There is some linear combination here which will give me C2. So I can have some numbers here, A11 up to agreed. This is the definition of, in some sense, is saying that column rank is K, right? Because there are K vectors which I have picked from here, and there are some linear combinations which make it M, right? And now, yes, now you just view it differently. You can write this as row 1, write this as row 2 as Rk. Okay. What is the first row of M? It's the linear combination of R1 to Rk with these coefficients. What is the second row of M? It is the linear combination of R1 to Rk. This is just understanding what your matrix multiplication does, right? So when you write AB equal to C, you can view it as, you take the columns of A, multiply it with the coefficients in the first column of B, you get the first column of C. Or the other way to put it is, you take the first row of A, multiply it with the rows of B, you get the first row of C. Okay? So then, I just think of them as K rows, and I see that every row in M can be written down in terms of K vectors. That proves that if you can show that every element of M, you can write it in terms of, every row can be presented in terms of K vectors, that shows that, what does this show about row rank? Row rank is less than equal to column. Okay, because this need not be linearly independent. But then you can run the same argument in the opposite direction. Okay, so we had all these, we have all these nice things, and this allows us remember our old problem, we wanted to find out solutions of Ax equal to B and B equal to 0 is in some sense the simplest case. This is talking about the kernel of